and he will talk about the introduction to neural network compression technique. Nikolai, please continue.
Yes, thank you very much. Hi, my name is Nikolai Solmsdorf, and now it's my pleasure to give a comprehensive introduction to neural network compression techniques. Before I begin, a short word of introduction. I am an AI software solutions engineer at Intel, and as such, I'm responsible for providing software engineering for AI workloads and consulting on this matter for Intel's customers. Furthermore, please take quickly note of our disclaimer. For example, results and performance numbers can vary. So, very well, let's get started and look at today's agenda. In detail, I'm going to talk about the following. First, I will present a brief introduction to the topic, specifically addressing the question, why would anyone think about compression techniques in the context of neural networks? Then, I will walk you through a selection of some of the most popular techniques for optimizing a neural network, after which I will introduce to you a software tool that offers a plethora of such compression techniques and optimization opportunities in one toolkit, and that is the Intel Neural Compressor. Finally, this presentation will be rounded off with a short live demo of a neural network optimization. So let's get started with the introduction. So the question is, why would one actually think about compressing a neural network? That is there a need to do so? To answer this question, in this presentation, we will be examining a showcase, that is a particular deep learning architecture, the transformer. First, in order to give you a quick primer on transformers and for the sake of brevity, without going into too much detail here, are some salient facts. The transformer was developed in the context of machine translation, NLP, with an encoder-decoder architecture, and it was quickly adopted to other deep learning tasks and domains. Its core component is the multi-headed self-attention mechanism, and one huge advantage is its ability for parallelization. Most commonly known is probably still BERT, which is standing for bidirectional encoder representations from transformers. However, BERT is already some 4 years old, and the recent development saw ever larger models with hugely increasing numbers of parameters. While the underlying methods have not changed dramatically, the recent scale of model size and data have enabled unprecedented and sometimes unexpected capabilities, driving major improvements in language understanding, generating creative texts, multilingual translation, and so forth. However, while large language models are becoming more powerful, they are also becoming increasingly hard to use due to their huge size. And to exemplify this, quickly glance over these numbers from the well-known GPT-3 model. Admittedly, this is an extreme example, and one integral question with these oversized models remains, that is this kind of over-parameterization actually justified by the degree of improvements brought about in certain tasks? For example, does an increase of a couple of points in accuracy justify 3 times more parameters, as is the case going from BERT base to BERT large? However, even such smaller models, for example BERT, which by the way still prevails as a very popular NLP transformer model, Even such smaller models need a large amount of resources, especially for training fine-tuning. That is to say, despite their remarkable capabilities, the model's large size creates latency and cost constraints that effectively hinder the deployment of applications on top of them, both on server and client devices, which in total amounts to the question, who can actually make use of such models? So in summary, and hopefully answering our question from the beginning of this presentation, this goes to show that there is a good reason to think about how we can optimize and compress these powerful models. That is, on the practical side, we want to make them faster, computationally efficient, and last but not least, also more sustainable. And while transformer architectures might represent an extreme showcase, this basic reasoning, of course, also holds true for other domains and architectures, for example, CNNs in computer vision. With this in mind, let's turn to the compression techniques proper. And for this, we will be talking first about data type precision, then quantization, pruning, knowledge distillation, graph optimization, and mixed precision. First, however, let us briefly revisit this important basic aspect of many compression techniques, which Akash touched upon before, and that is precision. The basic concept of precision is quite simple. That is, it designates the number of bits used to store numerical values in computer memory. Some of the most common types found in deep learning are int8, which uses 8 bits, Google's BrainFloat 16, which takes 16 bits, as does FP16, NVIDIA's TensorFloat 32, which, contrary to its name, uses 19 bits, and FP32, which takes up 32 bits. In some more detail, most commonly computations in the context of deep learning are done in FP32, with the sign as the first bit, an 8 bits exponent, and a 23 bits mantissa. This is basically still the standard in deep learning. An efficient replacement for FP32 is BrainFloat 16. This type was designed by Google specifically for deep learning as a simple truncated version of FP32. It has the same exponent as FP32, only the mantissa is truncated from 23 to 7 bits. Through it, a 2x performance speedup can be observed with a minimal loss in accuracy against FP32. It allows for faster training, mixed precision training, to which we will come later, and inference. int8, on the other hand, is not suitable for training, but recommended for inference when a small loss in accuracy is acceptable. Here, significant speedups can be observed compared to FP32 inference. In summary, through a smaller precision type, we can make sure that memory bandwidth as well as storage is lowered, whereas at the same time, we can achieve performance speedups, such as faster inference. However, the trick is to do all of this with a minimal loss in accuracy. Now, what about the actual techniques for compression? For example, for lowering the precision. This takes us to quantization. Simply put, quantization is the systematic reduction of the precision of all or several layers, that is weights and or activations within the model. Effectively, this reduces the total model size, but possibly at the expense of accuracy. This is a well-tried compression technique which foremost allows for faster inference. As the standard precision for deep learning computations is FP32, the standard quantization reduction aims at int8. Please note, extreme quantization, that is, the use of even lower bit widths, such as 4, 2, 1 bits, for example, ternarization, or even binarization, is an active, albeit challenging field of research, which has also shown great progress. However, the standard quantization procedure goes as follows. The higher the precision, the wider the dynamic range of representable numbers. Thus, FP32 is more versatile because it can represent more numbers. Now, when you quantize your model, you essentially map the wider full precision range to a smaller integer range by means of a scale factor. That is, you multiply the floating point value by the scale factor and round the result to a whole number. For determining that scale factor in turn, there are various quantization approaches or techniques. In a nutshell, three different techniques are most commonly used. First, there is post-training quantization, in which, as the name suggests, the reduction of the precision happens without retraining. PTQ, in turn, is usually differentiated in static and dynamic post-training quantization. The former is very basic and also fast. It requires one additional pass over the dataset in which the distribution of the activations is used to do the calibration, for example, to determine the scale factor, upon which the conversion of the weights and activations from floating point to integer is based. In dynamic PTQ, on the other hand, no dataset is needed. Here, weights are quantized ahead of time, whereas the scale factor for activations is determined dynamically based on the data range observed during inference runtime. This ensures that the scale factor is tuned so that as much signal as possible about each observed dataset is preserved. Quantization-aware training, on the other hand, takes a different approach. Here, low precision computation at inference time is simulated already during training. That is, weights are trained while being aware that the model will be quantized eventually. Usually, QAT leads to higher accuracy compared to PTQ, but it takes more time to actually deploy such a quantized model. Hence, in summary, quantization is the systematic reduction of the precision of the model. One very common procedure in deep learning is to go from the standard FP32 down to int8. This can be done with post-training quantization, static and dynamic, or quantization-aware training, and it allows for a speed up of the inference step in a deep learning pipeline, yet it can result in a small loss in accuracy. Another highly popular compression technique is pruning. Pruning hinges on the simple idea that not all parts of a neural network are actually salient to a certain task. Hence, it aims at removing such superfluous parts to achieve more compact architectures. Most commonly, two different approaches are applied. Unstructured pruning revolves around finding the least important connections in the model. It simply amounts to reducing superfluous weights to zero in any part of the model, hence its name, unstructured pruning. Here, essentially, the network architecture is unchanged. However, a certain amount of sparsity is induced. That is, we add a lot of zeros to the model, which can be a challenge for hardware accelerators which cannot speed up such sparse computations. In structured pruning, in turn, whole groups or structures of parameters are reduced to zero, for example, filters or channels. This possibly can change the width of the entire network, and it must be made sure that the actual architecture is not changed too drastically. For example, when full layers get pruned, which can lead to layer collapse. The actual procedure of finding the least salient parts in the network and for limiting the harm on it, in both structured and or unstructured pruning, is determined by various pruning algorithms. And here is a non-exhaustive overview of some of the most popular algorithms. Skipping the minute details here, I simply highlight magnitude pruning, as it is one of the most common algorithms. Here, the weights are simply pruned by the lowest absolute value at each layer with a given sparsity target. As a side note, the idea that not all parts of a neural network are actually important is as simple as compelling. In its final consequence, one could assume that there is actually a much smaller, streamlined version of a given neural network where all superfluous parts are removed. That performs as well as the bigger, bloated counterpart in both training and inference. Finding the lightweight version through pruning, in turn, was likened to winning the lottery. Just imagine having the power of GPT-3 in a much smaller package and coming up with the corresponding winning lottery ticket, that is finding an optimal subnetwork, is an active and fascinating field of research, which, by the way, was actually referred to as being like a gold rush. Moving on and summing things up, pruning aims at getting rid of superfluous parts in a deep learning model. Typically, it is differentiated between unstructured and structured pruning, and here too, typically, faster inference is the goal. However, a small loss in accuracy can be expected as well. The trick being how to prune the network with limited harm. A very different optimization approach, in turn, is taken in knowledge distillation. This is a compression method in which a smaller model is trained to mimic a pre-trained larger model. Typically, the larger model is referred to as the teacher, whereas the smaller one is the student. The general workflow of knowledge distillation is shown in this graph. The teacher model will take the same input as the student model. The output, in turn, contains the knowledge of the teacher, which is eventually transferred to the student via a combined loss function. Hereby, the student model most commonly is a shallower version of the teacher. However, and now slowly putting together various optimization techniques, it can also be quantized or pruned or by means of neural architecture search optimized version. Coming back to the showcase of this presentation, one very popular transformer model where knowledge distillation was successfully applied is Distilbird. Here, the student is 40% smaller than the teacher, that is bird base, while it retained 97% of the performance in text classification, together with a 60% speed up at inference. Again, in summary, in knowledge distillation, a student network is trained to mimic a larger, more powerful teacher. Hereby, typically, the student is a shallower version of the teacher, and the knowledge from the teacher is transferred through a combined loss function. The thus trained student model, in turn, can be used for downstream tasks, resulting in performance gains in fine-tuning and inference. The concept of graph optimizations, on the other hand, centers around the idea of a neural network represented as a directed acyclic graph. And optimizing a deep learning model from a graph perspective is actually quite straightforward. It covers not only the graph and its operators, but also the runtime. That is to say, from the operator perspective, the graph optimization contains operator fusion and constant folding, whereas from the runtime perspective, it is about operator scheduling, computation resources, and memory management. In operator fusion, for example, the optimization procedure detects where in the neural network graph certain kernel computations can be fused together so that memory is addressed less often. Popular fusion patterns for FP32 and bfloat 16 are shown here, whereas for int8, this is an overview of the most common fusion patterns. To sum this up, graph optimization relies on the idea of a neural network as a directed acyclic graph. From this perspective, the graph itself can be optimized, that is, operators can be fused, which in turn also brings about memory optimizations. In general, graph optimizations lead to a faster inference step in the deep learning pipeline. Now, in a previous slide, you've already seen a combination of two precision types, that is FP32 with BF16, which takes us to mixed precision. As the name suggests, mixed precision is a combination of different numerical formats in one computational workload. Here too, the benefit is that this requires less memory and thus allows for both faster training and inference. Most typically, what we understand here is a combination of the standard single precision format, FP32, with the optimized half precision format, BF16, which, as we recall, is simply a truncated version of FP32. This speedup results then not only from the reduction of memory, but modern accelerators also can run BF16 operations faster, as they have specialized hardware on board to run such 16-bit computations, such as the advanced matrix extensions or the AMX instruction set. Now, in this regard, one particularly convenient optimization technique is auto-mixed precision. This hinges on the idea that particular operators in a neural network are much faster with the half precision format, such as convolutions, whereas others still require the dynamic range of FP32, like pooling operations. And as the name suggests, AMP determines automatically which operators profit from a conversion, which can function as fall-through operators. That is, a conversion is possible but does not bring a benefit, and which operators need to stay in FP32 for the time being. As mentioned before, this optimization can bring benefits to both training and inference. In summary, mixed precision refers to the combination of various precision types in one computation, and a common combination one finds is FP32 together with its truncated version, BF16. Thus, an elegant application of such a combination is auto-mixed precision, which allows for faster training as well as inference. And this concludes my brief overview of some of the most popular compression techniques. Now comes the question how these can actually be applied in your AI workload. To answer this, in the following, I will present a software tool that allows you to do so, and that is the interneural compressor, or in short, INC. The interneural compressor is an open source library which delivers a unified interface across multiple deep learning frameworks for popular compression techniques such as quantization, pruning, merge distillation, graph optimizations, as well as mixed precision. On the practical side, this top-level overview of INC shows you that you basically can take your model from any deep learning framework or model representation, that is TensorFlow, PyTorch, OnNX, or MXNet, and apply all sorts of optimization techniques. Excuse me. Hence, it supports different types of quantization, post-training static or dynamic, quantization-aware training, different pruning strategies, knowledge distillation, mixed precision, and further different tuning strategies, such as multimetric optimization. Please note, we've now learned that potentially some of these techniques can impact the accuracy of your model, for example, quantization. However, INC is designed as such that it uses automatic, accuracy-driven tuning strategies to help you easily and quickly find out the best optimization methods. All in all, it's a really powerful toolbox that runs on both CPU and GPU. Hence, a simple example of how you would perform static post-training quantization with INC goes as follows. Here, quantization is an iterative process. That is, first, you need your FP32 model, a data set, and the corresponding evaluation metric. Next, with INC, you calibrate, quantize, and evaluate the quantized model. This is repeated until a certain accuracy goal is eventually met. And please note, you yourself can configure this in detail. That is what the next iteration should be according to various tuning strategies, such as Bayesian, randomness, or you can plug in SIGOPT. That is our sophisticated hyperparameter tuning tool you met this morning. One a particular success of INC I would like to single out is the adoption of our tool by the well-known transformer repository Hugging Face. As you all know, Hugging Face slowly but steadily developed the go-to library for transformers. There, not only a growing numbers of models are hosted, but also a large selection of datasets. Furthermore, as the transformer architecture, meanwhile, was also successfully applied to computer vision, one finds a variety of computer vision models or even multimodal models, Q, Stable Diffusion, on Hugging Face 2. So, in a nutshell, Hugging Face is quite successful and has become the reference for transformers. And in 2021, they released Optimum, that is a toolkit for compression techniques, and which includes essentially a wrapper for the interneural compressor, which in turn also bespeaks the acceptance of our tools in the AI dev community. So, to sum things up, INC is our all-purpose model optimization tool, which includes the most popular compression techniques such as quantization, pruning, knowledge distillation, etc. Even though in this presentation emphasis was put on transformers as the showcase, INC covers all sorts of deep learning domains and architectures, including computer vision, recommender systems, etc., etc. Now, speaking of our showcase and rounding this presentation off, let us quickly switch to a short demo. So let me quickly start this. What we see here is a quick and simple example of how to perform static post-training quantization with INC. In particular, this is done with a Distilbert model on the MRPC task, that is text classification, using the Hugging Face API. So, please note, as mentioned in my presentation, Distilbert is already a highly optimized model. Please think back to the knowledge distillation section. However, here we will showcase that through PTQ, using INC and very little effort, we can even speed up this highly optimized model for inference with only a minimal loss in accuracy. In some more detail, what we will do here is, first, we load and pre-process the dataset from the Hugging Face dataset hub. Next, we set up and evaluate the FP32 text classification model with the Hugging Face trainer API, after which we quantize the FP32 model to an int8 model using INC. Also, we evaluate the quantized model. And finally, we compare the two models against each other with respect to accuracy, the model size, and inference latency time. As a side note, this notebook is running on an Intel server machine with a third generation Xeon accelerator on board, which, for example, comes with the AVX 512 VNNI instruction set, speeding up vector computations. So let's get started. And while we wait for this notebook to finish, Yes. We switch to this copy, which already ran, and I spare you the details of the setup, pre-processing, and the like. Instead, we immediately jump to this. Here, we evaluated the pre-trained FP32 model that comes directly from Hugging Face. Thus, we ran inference 10 times to get some robust numbers, and we can observe an accuracy of 84.75%, being our baseline henceforth. Next comes the interesting part, and that is the quantization with ink. As mentioned before, for this, we need the FP32 model. Here, a dataset called here, and an evaluation metric, which is here. Furthermore, we also need a simple configuration YAML file, which is loaded here, in which we can set some simple hyperparameters for the quantization procedure. Most importantly, so this is what the config file looks like. Most importantly, here we define how much accuracy we are willing to sacrifice for the quantization. Then the iterative quantization procedure itself starts and runs until the algorithm has found a model which meets our demands. And this can take a bit of time. And in this case, scroll, scroll, scroll. It is finished here after 33 iterations. For your information, Ink provides detailed feedback on which layers got quantized. So for example, in this case, we can see that all layers but the layer norm and one linear layer were quantized. So, very well. Let us examine what we got and compare the FP32 model with the quantized Int8 model. And first, after running inference again, now with the quantized model, 10 times, we can see that the accuracy actually dropped, but just the tiniest bit, that is 0.5%, which is not bad, but still a price we pay. However, here it is visualized that in this case, this discrepancy is actually not that grand. Nevertheless, what do we pay this drop in accuracy for? Did we actually achieve something by the quantization? Hence, let us next look at the respective model size and observe that the Int8 model is actually a lot more compact than the FP32 model. That is, it is about 3.5 times lighter. Not bad, I'd say. However, this can be kind of expected since the quantization, that is, the reduction of the precision from FP32 to Int8, and please remember, this equals a reduction of bits used in memory, naturally leads to a smaller size. So even more importantly, maybe, what about performance? Is the quantized model actually faster? For this, let us quickly compare the inference times between the two models and again observe a welcomed performance boost. That is, the quantized model is indeed 2 times faster in inference than the FP32 model. So summing things up, without a lot of effort using ink, we were able to significantly reduce the size of the model and also speed up inference. And please recall, this is on top of an already highly optimized transformer model. And by the way, in the meantime, the other notebook, yes, has also finished its computations, showing us that the overall process of quantization can be indeed quite simple and swift. So with this, I finally arrived at the end of my presentation. And I thank you very much for your attention, and I am looking forward to your questions. Thank you. Thank you very much.